Hi everyone. I hope everyone's recovered from yesterday's lecture. Apologies that, it was a bit of a nightmare. I hope your brains and ears have recovered from the sirens. Today we're going to have our second attempt at doing basically the same content. I'm not going to go through that particular slide that I started about 3 or 4 times. I think I finally got there yesterday. As always, there's live lecture code. A few different announcements today. Next week, in your lab time, your regular lab time, there's the week 8 lab exam. And this is really just for you to help you prepare for the final invigilated exam. So it'll be in actual labs and it'll be in the exam environment that you'll have in the real exam. And it'll also help you work out how you're going and how you're sitting with the array content, which will be a hurdle in the final exam. So please attend your week lab class as scheduled. Make sure you're there in time. Obviously, you should be at the tutorial first, but make sure you're getting to that lab on time so you can start that lab exam. Now, online classes, you'll get some more information if you haven't already about what will happen for you. But yeah, don't stress about this. This is worth 1 lab mark. If for some reason you can't make it because you're sick or for some other reason, please just email the course account. Okay, you don't need to apply for special consideration or something, but please email us. So for week 8 lab marks, there'll still be some regular exercises. There'll be 1 dot, 2 dot, and 3 dot, and all up they'll be worth 1.5 marks, and the actual lab exam part will be worth 1 mark. And this isn't based on you getting 100% of the coding correct. This is based on you turning up and submitting a solution for at least 1 question. So it's really for your benefit. There will be 4 questions. 2 of them will be array hurdles and 2 of them will be debugging. So, I mean, don't be too hard on yourself if you don't get the whole 4 questions out in the hour, but yeah, it's really a good way to see how you're going with the array hurdles especially. Okay, so yeah, your performance is not marked. As long as you've made an attempt and submitted something, you'll get that 1 lab mark. All right, so that's for next week. Yeah, last lecture, we did not get very far, and I've already apologized. So we do have our extra catch-up lecture tomorrow evening from 5 to 7, live streamed on YouTube. There should be links on the course website. So, basically today we're going to do the lecture we were supposed to do yesterday. Tomorrow we'll do the lecture we were supposed to do today to get through all the important content. So again, we will do a bit of a pointers recap, and then we're going to talk about pointers and arrays, which we didn't finish back in week 5. Then we're going to learn some new stuff. So let's just get started on this again. So I think we're about to do this exercise. This is just to check that you're on top of the basic concepts of pointers before we move on and do some more things. So we could compile this code and run it, and it's going to print out something, but we want to also be able to reason about what it is actually doing. So basically, and once we're at this stage of the course, if you haven't already been doing it with arrays, you're probably going to have to start drawing things when you're thinking about what's going on. Anyway, we've got some variables in this program. X, Y, PTR1, PTR2, and Z, and they're all stored at, they're all variables, they're all stored in memory. They've all got addresses, and yeah, I'll make some fake ones up. Again, these are not realistic for so many reasons that I don't have time to go into. but just to give you concrete data. Okay, so the first two lines are okay, I hope. We've got x equals 2, y equals 5, so we're just storing integer values in our variables. Then here, we've got a variable of this type here, int star. This means this is a pointer variable. This means it's allowed to store addresses of ints. So here we're storing the address of y, which, int y, it's an integer variable. We're storing the address in here. So in my example, this is my fake address for y. So let's assume it's this address. This is literally what this variable would be storing. And we think of it as that this variable is pointing to this one because it knows the address of it. Okay. And these aren't the real addresses you'd get if you ran the program. And the addresses where variables are stored change every time you run the program as well. Now the next one, this is another pointer variable. It's storing the address of x. So it's just storing this value where it knows, well, it's asked x, what's your address? It's storing it. So it's like it's got a pointer to x. So this is what we've got so far. Now down here, we're doing some kind of calculation and we're putting the result back in Z. And always when we're working with assignments in C, we need to just start on this right-hand side and evaluate it. So star PTR1, well, PTR1 itself is the address. But if we do star PTR1, we're actually going to that address. So we're going to this address where y is in this case, and we're getting the value 5. Then when we say star PTR2, we're going to that address that's stored in PTR2, and we're getting the value 2 out. Okay, so that's called dereferencing the variables. We're going to those locations and getting the values out there. So when we add that up, that's equal to 7. And we put that into Z. I hope everyone's sort of following. Down here, we've got Z times 2. Well, that's not too hard. That's 14. And now we're storing it back. Where are we storing it? Well, not in PTR2, which would be, here. We're not storing it there. We're going to that address that PTR2 points to, and that's where we're storing it. So now we're changing this value, to 14, right? PTR2 pointed at x, so we're going and changing the value of x basically, indirectly. So this is the kind of stuff we've got in memory right now. And when we print it out, well, we're printing out x, which should have, by my calculations, 14. Y should have 5. Z should have 7. PT1 is pointing at y, so star PT1 should give us 5. PTR2 is pointing at x, so star PTR2 should give us 14. I hope I haven't done anything silly. Let me know in the chat if I have. Okay. Now we do this line here. So there are no stars here. It's not star PT1 or star PTR2. We're literally talking about these variables here, and we're just taking the contents of one and putting it in the other. So basically the address that's in PTR2, we're storing it in here, which basically means now that PTR1 is also pointing to x, right? So when you do something like this, you're making pointer 1 point to the same place pointer 2 was pointing. So now both of our pointers are pointing at x. Okay, so pointers can change where they're pointing to. Their variables, those addresses can change. All right, so now if we go down here and print all this stuff out, well, we haven't actually gone and changed any of the integer values, but now when we do star PTR1, it's pointing to X, so that's going to print out 14. Star PTR2 is still pointing to X, so it's still going to print out 14. All right, so this really just puts together all of these concepts about addresses, initializing pointers, dereferencing pointers together. So hopefully that makes sense. You can run it to check I got the right answers. Actually, let's do that together. If I've done something wrong, it's better that I find out and fix it now, right? So is that what I got? Oh, hang on. Yeah. Yes, that's what I got. But yeah, you can play around with this code, change things, see if it does what you expect it to. Could I make an address equal to 5? Well, the thing is, we don't know the actual addresses of anything. So we never want to hard code any addresses in our code. We are always just asking for the addresses of things that already exist, for example. So if we just say, let's try and make this point to address 5, that's probably not going to compile. Yeah, it's not going to compile because it's saying, hang on, you've just typed in some int. Okay, and even if it did compile, we'd want to be very careful, about just randomly choosing an address when we know nothing about where the addresses, what actual real addresses are being used in this program. So yeah, you'll never hard code the addresses in. Okay, so that's pointers. Now, the reason that and when we print out our pointers, they're printed out, or when we write them, they're printed out in hexadecimal. Pointers can equal other pointers, or they can have the addresses of variables. We'll see another thing that they can have later as well. Yeah, but it can only contain, a pointer can only contain an address of something else that's existing in your program, and you can't just make up random values for it. Okay, now why do we typically use pointers? Well, we had a look at this code before, and even though this code might look like it's got two variables x and y that are being modified by these functions, we found out that that wasn't the case, and that this program, nothing modifies, these functions don't modify these original variables. And if we run this, we'll just keep getting 2 and 5 printed out. So just a reminder, because we'll be going into the heap today, so just want to make sure we're clear on the stack. The stack is just a part of memory, so part of RAM, and this is what's storing our variables. It stores some other things as well to help with function execution and returning, but we're just really focusing on local variables. But every time our functions finish, the data that they store on the stack gets popped off or removed, and those variables don't really exist anymore. So here's an example that we looked at. Imagine we've got our main function, and again, I'm sorry, I've put the functions on top of the main, which is bad style in my slides. Anyway, basically the main will be the first function that you're running in your program, and so that'll have a location on the stack for its local variables, and in this case we've got x and y, and we're setting their values to 2 and 5. But now we're calling another function, update, and we're passing in copies basically just the values 2 and 5 get passed into that update function, where by chance they're also called x and y, because this is a situation that particularly confuses people. So that's why I gave them the same names. So we're passing in 2 and 5, but in that update function, when that gets called, it gets its own little chunk of memory on the stack as well. And we call these things stack frames. So we've got a stack frame for the main, a stack frame for update, and they all have their own separate memory locations, all of these different variables. I haven't drawn in fake ones. But basically, the variables that are in our update function, even though they've got the same name, they're stored in separate memory locations. They're not the same. They're just copies with the same values, and the variables happen to be the same name. That's how C works by default. It just passes in copies of the data. So in update, we're going through and we're modifying our X and our Y, but we're modifying the local copies we have. Okay, so just, if I gave you a copy, I sent you a copy of a file and you changed it, my original hasn't changed. Anyway, once we finish this update function, it gets popped off the stack and we're just left with our original X and Y, and that function did not even touch them. They're just exactly as they were. So we still have 2 and 5. Then when the main finishes, even that gets popped off the stack, but then your program's about to finish anyway. So that's how the stack works. It's very handy because it really takes care of our local variables for us. And it even protects us from functions modifying things when we don't want them to. But sometimes we might want a function to be able to modify our variables. And that's where pointers can come in handy. So we know that scanf modifies our variables. Like we might pass in the address of X to scanf. Scanf goes and places a value in our variable for us. So we can do something similar ourselves. We can pass in the addresses of our variables to functions. Those functions then have to be written in a way that allows that. So they need to have pointers as their parameters or inputs, because pointers are the types of variables that can store addresses. And then once we've got pointers, if we want to go back to those values, so let me just draw this. So here, instead of passing in the value 2 and 5, which is just copies, it's passing in the addresses of these original variables, right? And that's what we're calling X and Y in the update function. So down in here, if we want to modify these original values, we're using *x. We're going to the thing it points to and we're adding 1. So we'd really be modifying this original value. We're saying *y, so we're going to that original value back in the main and modifying it, okay? And this is because we know the address. We could go to that address by dereferencing our pointers and change things directly. And then when that function finishes, those changes were made permanently on those original values. Okay, so that's one of the best things about pointers. Oh, here's a better diagram than the one I just scribbled, I guess. The stack frame for main will have the X and Y, the original ones. We pass in their addresses, so we've got pointers to them in the function. The pointers in the function can be used to directly or indirectly, I guess, access those variables and change them. Okay, I hope everyone's okay with that. And then we looked at how we could go and change this swap function as well. I'll leave that to you to look at later. We looked at it in week 5. All right. I'm just checking the chat. All right, then the next thing is, well, that's the way by default things work for integers, doubles, chars, but also structs. So if I pass a struct into a function, it's the same thing. The function is getting a copy of the struct. So if I've got 10, 9 in my struct, imagine it's got an X of field and a Y field. So I've created a struct point. I've set the fields. I pass it into update, but update has its own copy. This is also the way structs work. And you would have seen this in your assignment if you did try and pass in any structs to functions in your assignment and then you tried to modify them. You might have realized that, hang on, this just isn't working because it's modifying the copy. You know, it finishes and this original copy has not been modified. Did anyone have that issue in the assignment? That they maybe tried to put their code in functions and suddenly the structs weren't updated and it didn't work, and maybe, yeah, someone did. And now you possibly, yeah, I bet lots of people did. And you possibly, if you've just really got one struct you wanted to change, one option is you could return it. So that's one option. So here's an example. Instead of having a void return type, I could take my copy of my struct, right? I've got my original struct here. I've got a copy. I'm changing my copy. But then I'm returning it. So down here, we're returning this copy and we're assigning it back. So when we do that, this copy gets copied back into the original one. So yeah, we're able to do it in this case because we can return one thing from a function. And in this case, if it's just one struct, we could return it like this, make sure we assign it back. And that's one way we could do things, which probably worked well in the assignment. There's still some cases where we might want to modify like more than one struct, or modify our struct and return an integer, or I don't know, there's other scenarios where we might want to use pointers to do this. So we could write something like this. Again, instead of passing in a copy, where's my pen stopped? Okay, this is my point. Instead of passing in a copy, I'm passing in the address. So now this function has a pointer or the address of this struct. And you may not have remembered this. If I've got a pointer to, if I've just got a struct, I use dot to access the fields. If I've got a pointer to a struct, I use arrow to access the fields. All right, so I can say p arrow x equals p arrow x plus 1, and I'm going into this original value. I'm going to where this points and changing that value inside it. And I'm doing the same thing for y. And then when this finishes, I've really updated this original struct. Yeah, and somebody's asking about the alternative way. So let's see if my pen works now. Yes. So usually if I've got a pointer to something and I want to go to the thing it points to, I dereference it like this. So that would take me to the whole struct. Like if I had a pointer to this struct, star p takes me to the whole struct. So I'd want to do that first. And then I would use dot to get to the individual field. That's how I could do it instead of using p arrow x. Now the problem with this is we've got to make sure we dereference it first and then do the dot. And if we don't put these brackets in, the order of operations in C does it the other way around and it doesn't work. So it gets annoying to do it like that, even though it works if you do it properly. And this is typically what people expect, how people expect you to do it with the arrow. It's easier, and it's sort of, once you get used to it, it's the more readable way that it's usually done. But logically, it's doing that same thing, dereferencing it, and then getting the field. Whenever we're passing in the address of anything, like whenever we've got to supply a pointer, if we've just got a regular value and we need to pass in the address of it, that's what we use, %p. If I tried to pass in p, I'd just be trying to pass a copy of my point in rather than the address of my original point. Okay, just like with scanf, %d or whatever, any of our scanfs, we've got that ampersand, we're giving the address, so the function can go to that address and update things. Okay. And there's the code for all these things available that you can go and try. Now, the exception to all of this that we've been talking about are arrays. So again, in the assignment, you might have noticed that you were passing arrays into functions, but they were being updated by the functions, whereas your poor structs weren't. So by default, without us having to do anything at all, when we pass an array into a function, by default, what actually gets passed in is the address of where that array lives. So this is why, without us doing anything the whole time, functions have been able to modify the contents of our arrays. It doesn't send copies in. This is just the way they designed C to work. And that's why we can modify our arrays in our functions. So if we go to this kind of example, right, similar scenario, I've got some variable in the main or wherever it is, and I want some function to change it, but here I'm just passing in nums. And basically, if we kind of just learnt what we did before, we probably might expect that this wouldn't work. It might be a local copy, but it's not. The way arrays work, we're always passing in a pointer to this array just by giving the name of the array. So the name of the array really tells us the address of that array. So because we've got the address of the original array, when we go through here, we're actually going to these locations. And you might be thinking, oh, but we don't even have any stars or anything like that. But the way indexes work with arrays basically is designed to be an offset from an address. So you're saying, well, go to the nums array, and we've got the address of that. And then, you know, if we're at index 3, go 3 integers away from that address, or whatever type you've got. And it can do the maths and work out the exact address based on this sort of index or offset. So that is what C is doing behind the scenes. It's doing sort of address operations with these I indexes for us already, without us even having to have really understood it at that level. So yeah, so the thing maybe I should have pointed out first is, yeah, I'm in the wrong directory. Yeah, so this does increment it because arrays are passed in with a copy of their address. And then the function can go to that address and access all of the elements inside it. So yeah, increment does modify them all. All right. Now, this next example, this isn't something we usually typically have to do. I'm printing out a bunch of addresses. Oh, I deleted all my comments from this so it would fit on the one screen, but I meant to put them back in. Anyway, So in this example, this is just to help understand a little bit, right? What's going on. So I've got an array in here, and it is a bit deceptive really, because it's the max length is 5. So it really looks like this. But I'm going to run it and let's just go through what it does. Again, this is not doing anything but trying to illustrate what's going on. Now we're seeing lots of real addresses here, but again, I'll just say if you run it again, you won't necessarily get exactly the same addresses. But anyway, the first thing we're printing is this printf here, and it's printing out, it's just printing array. Well, the name of the array, when you go to, like anytime you are talking about the variable name of an array, that's basically the address. So this is already giving us the address of the array. We don't have to put an ampersand. The array itself is the address of the beginning of that chunk of memory. So the array is starting here at this address. Here I've got a while loop. It's going through every single element in the array and printing out the address of that element. So the address of the first element in the array is basically the same thing as the address of the start of the array. Hopefully that makes sense. Then we can see, now these numbers are very long, but if we look at the last 2 digits, we can see that this one's at an address ending in 80, the next one is 84, the next one's 88, the next one is 80C, which means C means 12, and now we're 90, which when we wrap around in hex, we're back to 16. But basically, these are all 4 apart. So these are all integers. They're at addresses 4 apart because this is like a contiguous structure. It's an array. There's no gaps in there. They're all just squashed in right next to each other, which is why we can use those indexes. So yeah, and if you try and print these addresses out, you don't typically want to do this for a real program that people are using, unless you're writing some sort of debugger or something. Now down here, there's 2 functions. These are just printing the contents of the array. And the prototypes, if you look at them, it makes it look like these are very different prototypes, right? One says int star nums, the other says int nums in brackets. These are both ways that you could write prototypes for things that take in arrays. Style-wise, you might really, like this one better because it looks very familiar, but it'll do the same thing. When we pass in the array, again, this is the address that we're passing in to this function. This same thing is the address that we're passing into this function. So either way, it's going to do the same thing. And either way, in these functions, we can still use indexes because that's what the indexes do. They go to offsets from an original, a starting address. So this is sort of behind the scenes. You don't have to know this much detail to succeed in this course, but it is nice to sort of understand what's going on in the background. So if you found this completely confusing, it's not the end of the world. You can come back and look later, but don't sit there panicking about it. All right, one more thing about arrays and pointers. And again, this is another tough example. So if you think this is tricky, again, don't start panicking. Okay, so I've just got a normal array with these characters in it. And we know that if we do something like this, C will go and put each character into its own cell in an array, and it will put that null terminator at the end. So that's, because remember, strings are arrays. They're just sort of special arrays that have chars and a null pointer. So this is what S is looking like in memory. Okay, but now we've got another variable called SP. And we're saying, let's store the address of this here. So S is our array. If we go to S at index 1, you know, that's this chunk of memory here. This pointer is pointing to this chunk of memory here. Right, so we've got a pointer that's basically pointing partway through an array, which is perfectly fine. Is everybody happy up to here? Now, having done that, I'll give you a moment to have a look. What do you think it's going to print out? What do you think this is going to do? Line 8 or line 9 or line 10? Someone wrote ointers. Yeah, one of these lines does basically print out ointers. But on line 8, we're saying, this is just like using the rules of pointers. We're printing out one character. What character are we printing? Well, we've got the address of some character in here. We're going to that address and printing it out. So yeah, in this case, we should be getting an O. This should print out an O. Because this is where we're pointing. We get the character that's living there. It's an O. Now, this is exactly the same thing we get if we use this index notation. So keep in mind, we're indexing S now. So in a way, we're treating we're indexing SP now. We're treating SP kind of like a pointer to this sort of substring or subarray. But indexing, you know, we go to this address and we move 0 characters away. That's what this is saying. We're still going to get O. If we go to this address and we move 1 character away, we're going to get the I. All right? If I said SP at index 3, we'd be going to the address where SP is pointing, and we'd be going 1, 2, 3 away. So we can point somewhere in the middle of an array or a string and start using indexes from there, as though where they're pointing is basically, you know, the index 0. Okay, and yeah, if we don't have to give this a size, if we initialize it, it'll make it exactly the right size to fit the string. Sometimes we put sizes in here, we might want it to have extra room, but in this case, we made an array just big enough for this exact string. Now down here, SP is not really a string. SP, let's just go back a step. SP is a pointer. SP is just storing an address. So imagine if the address of this whole array was OX, I'm just going to make it 1,000. Well, these are characters, so this would be 1,001, 1,002, etc. This is just storing an address. And that address that it's pointing to lives in a string. Okay, so now if I've got a pointer to this character and I try and print out that whole string on line 11, yeah, that's where we're going to print ointers, because that's what printf%s does. It takes an address and it just starts printing out characters one by one until it gets to that null terminator. So this should print out ointers. Okay, so let's just, I'll get rid of some of my scribble. So first of all, I've got SP. it's storing the address of my array at index 1, which is here. If I go to that address and print out the character, I get 0. If I go to that address and jump 0 characters ahead, I also get, I should say O, the letter O. If I go to that address and jump 1 character away, I get the I. If I just go and print the whole string that starts at this address, I'm going to get pointers, which I don't know, for whatever reason sounds horrible. And then this is just an address, right? It's a pointer. I can change it and say, actually, I don't want it to point here now. I want it to point to the one at index 8 in the original array. So the original array starts here. So now my SP would be pointing here. I'm saying go to S, get the address of that 8th index item, and that's where this is going to point now. Oops. That should have been like 1008 if it's pointing here. So now if I print out this string, what am I going to get? Yep, it's just going to start printing out the string from here. Now this is quite advanced, and if you understood this, that's amazing, very well done. This can come in handy sometimes when you're dealing with strings, when you do want to maybe refer to some part of the string or a substring or something like that. But, you know, it's also an exercise in, I don't know, hurting our brains with pointers. Just one word of warning, if I've got an array S, right, S refers to, S is not a pointer variable. We can't just go around changing the address that it points to. Like we can with a pointer. All right, so you can't do something like this. Right? You can change where a pointer variable points. You can't say that my array suddenly, you know, starts somewhere else. Okay. Yay. All right, so look, those examples were really tough. So anyway, well done for persevering. Let's see where we're up to. I've done that. So someone's just asked, so before, let me get my, so SP is a variable that can store different addresses, right? So first up, SP was pointing to here. It contained the value, say, fictitious value of the address here. And then later we decide, actually, I'm going to change that, and SP is going to point somewhere else. Because SP stores addresses, it can store different addresses. Now, S itself is not storing addresses. S is storing character data. S refers to a fixed address. So where we can make SP, which its whole job is to store different addresses, where we can make SP, which is a pointer point to different things, S stores char data. There's a fixed address that refers to this chunk of memory, and you can't change it. All right, so this is a very sort of subtle point that is like the difference between these things. All right. So we've looked at passing in pointers to functions, pointers to ints, pointers to structs, just arrays, we know now that they're passed in via, basically a pointer 2 without us even doing anything. But can we return a pointer from a function? And the answer is yes, we can, but not via the sorts of things we've done so far in the course. So let's have a look at these examples. Here, the name of my function is f, not a great name in real life for code. And my return type is int star. So this is the syntax for returning a pointer to an int, for example. And in here, I've got my x with the value 3, and I'm trying to return the address of it. All right, so out into whatever called me, I'm sending it this address. And the syntax here is great. That's an address that matches this type. That's all fantastic. The problem is this is a local variable that lives on the stack. So I'm returning an address of a local variable that is not going to exist anymore. So it's like me saying, here's the address, and when you get there, it's, being demolished. It doesn't exist. So this is a bad thing to do. In DCC, it's going to complain. If you do it anyway, it's going to crash. With other compilers, maybe sometimes you can do it, and you might get all sorts of weird results, or it might crash. This is the same thing over here, right? We have an array, and again, it's a local array, and we're returning it. And we just learnt that if I just say the name of an array and return it like this, what I'm really returning is an address. So again, the syntax of this is fine. It's just conceptually and practically what's happening is this is going to be stored on the stack, and we're returning the address of this thing that's about to be destroyed. So if your poor function tries to use it, it's not there, and the code will crash. So yeah, we can return pointers from functions, but not to local variables. And after the break, I think we'll talk about how you do it, okay? Actually, no, I'll do a little bit more. So the problem is we've got our local variables on the stack that we've been focusing on. They're automatically controlled by the sort of system. They're getting created and destroyed when we call functions and when those functions end. If we want to be able to return pointers from our functions, or create arrays that we can return pointers to, or create variables that we can return pointers to from our functions, we can't store the data on the stack. We've got to store them on a place called the heap. Okay, the heap is something that allows us to have complete control over the memory that we get. So unlike stack memory, the programmer decides. It says, give me some memory, and then that memory is available to use until the programmer frees it. It doesn't suddenly get destroyed when the function returns. So you can ask for memory on the heap from a function, do stuff with it, return a pointer to it, the function ends, it's still there. So that's what we can do with the heap. It's a little bit more work, a little bit more understanding to use it. But yeah, that's what we can do. So after the break, we'll learn how to use malloc so we can actually ask for memory that doesn't suddenly get destroyed. And, it also allows us to ask for memory basically whenever we like throughout our program, even if we don't know in advance how much we're going to need. So let's come back at about 2 past. Let's have a 10-minute break. We'll come back. We'll learn all about malloc. It's very important for our next topic, which comes up, which is linked lists. All right, so let's have a break and we can rest our poor brains for a little bit. and come back at 2 past. All right. So, yeah, we're going to look at a new function called malloc or malloc. It basically stands for memory allocate. So we use malloc and we ask it for a number of bytes of memory, and the memory that it gives us will be on the heap. So we ask for it, it's going to return a pointer to that chunk of memory. Or if there's not enough memory left to give us what we've asked for, it returns this keyword called null, which basically is a way of saying, you know, there is no valid address. And you've seen null before. I think fgets returns null if you press Control D. But yeah, it just means there's no address. It's a value you can give to a pointer, which means, yeah, nothing kind of thing. So when we do our mallocs, we should always check in case it returns null and it says, no, there's not enough memory. In the kinds of programs we're writing, it's going to be very unlikely that we do use up too much memory. But, you know, in the real world, you might, and you should just always check for it. In programs you write, if you've done something buggy, you certainly might run out of memory. Anyway, but malloc allows us, whenever we like, to dynamically create memory or ask for chunks of memory in the heap that will last beyond the end of the functions. And it'll last until either we say we don't want it anymore, or basically when the program ends, all the memory associated with it will be given back to the system. It's not like if you do your malloc and you know, don't tell the system you don't want it anymore. It's not like you've lost it forever or anything. Anyway, now to start using malloc, we've got a new library, stdlib.h, to include. I'll talk about the null pointer as it comes up. But when we're asking for memory, we don't just want to sort of do our own calculation and decide how much memory we need for something. So we don't want to think, well, I need some memory for a struct, and I've decided that I think that struct would take up 9 bytes. Because, you know, you might get it wrong for reasons that, you know, sometimes structs have little gaps in there or whatever. Or you might not just want to think, well, I know that my ints are 4 bytes, because that might be true of our machines at this point in time. But if we go to another machine or another system like an Arduino, maybe ints aren't 4 bytes. Maybe if we come back to the CSC machines in 10 years, our system would have been upgraded or something. Maybe our ints will be bigger. So we always want to use size of for anything, even if you think you know how many bytes they're stored in. Please just use size of to make your code work in other environments. And just in case you're wrong as well. All right, now this is more information than you need really, but size of itself gives us back a number, but these numbers can be much bigger than numbers that we store in int. So it gives back something called an unsigned long. You don't really need to know this, but yeah, a long can just store a bigger range of values than ints can. An unsigned value can only store from 0 upwards. It can't store negative, and it makes use of that range so it can store even bigger positive numbers. But honestly, just think of it like an integer, telling you how many bytes you're going to need when you go to use malloc. So putting it all together, I want to create an array of size 10 on the heap, an array of ints. So I just say, malloc, please give me enough memory for 10 lots of however many bytes we use to store an int. And yeah, on our system right now, at this point in time, that would be 40 bytes. And if malloc has 40 bytes, which we would hope it would, if that was all you were asking for in the whole program, it returns back the address of where those bytes can be found, but they're going to be on the heap, which means even if your function finishes, as long as you return a pointer to this chunk of memory, it'll still be able to be used. So that's using malloc basically. Now, when you use malloc, there's another function that you need to use as well called free. And the free function lets the system know that you don't need the chunk of memory anymore. So every single malloc that you do should have a corresponding free. Now, in some of the small examples we do, if we don't remember to do our free, our program's still going to run normally, and it's going to be okay. But in real world, sort of bigger, larger scale programs that might be running for days or hours or whatever, if the program keeps calling malloc and never does any frees, it will have what we call a memory leak, and it'll either run out of memory or slow down. So imagine you write a game and you keep doing mallocs, and somebody's sitting there devoting their life to playing this game. They've clocked up 18 hours on the game, but you're leaking memory and it's getting slower and then it crashes, or a website or a web server or your operating system, if they're slowly leaking memory, it's not good. But like I said, if we stop when our programs stop, the operating system does get that memory back. But we want you to get used to calling free in this course, even if you're only writing a small program that's not going to run out of memory. We want you to learn how to use free properly. And when you use free, you've just got to be very careful that once you've freed a chunk of memory, you're not trying to still use it. And we also don't want to free it again just in case, because that's sort of using it as well. So we want to free it once and only once after we've stopped using that chunk of memory. So putting that all together, typically we do a malloc. We typically check if it was successful. We go and use that chunk of memory because that's why we asked for it. And then when we're done, we call free on it. All right. Now, how are we going to know if we've done all of our frees properly? We've got an option in DCC, -- leak check. So once we start using malloc, we recommend that you compile it like this and check if you've got memory leaks. And I'll show you in a minute how we do that. And we'll also be running this on your code sometimes for assignments, labs, exams, in situations where we want to make sure you've done all your frees as well. So I know I just told you a lot of things. Let's try and put it together. So I've got this example here. This example is writing a function the wrong way that's returning an array. And I've got my local variable that's an array. I'm returning the address of it. We already know that shouldn't work. Let's try and compile it. And DCC warns us, you are returning the address of stack memory associated with local variable, blah, blah, blah. It's complaining. If we try and run it anyway, because we want to know what happens, or we think that DCC is wrong, it's going to give us a runtime error. Basically saying, hang on, print array is trying to print out memory that doesn't really exist anymore. So we know we can't do it like this. How do we do it? Well, instead of doing a local variable like this, we use malloc. So we know malloc is going to return a pointer. So now I'm making a pointer that can hold the address that I get from malloc. And in my malloc, I have to say how many bytes. Now, again, I don't want to guess the size of things. I'm going to use the size of, it's actually an operator. I'm going to use the size of and say, tell me how many bytes ints take up on this particular machine. And then how many do I want? Oops. I want this many. So this is going to give me basically, what's max? Yeah, about 40 bytes on this machine. But it's going to work that out, give me this chunk of memory. Then once it does, and actually I'm making a very bad assumption that it does and it worked. Is that 5? Okay. I've then got a pointer to it. And like we saw before, if I've got a pointer, I can still use indexing notation in it, right? So I can just do a normal for loop and initialize it to these values for whatever reason we want these values in there. And then I can go and return it. And I'm returning this int star. And basically now this variable up here has a pointer to this array. And this array is on the heap because we mallocked it. All right, so this variable here called data and this variable here called data these are both actually local variables on the stack that were pointing to this heap. So to begin with, we've got our data variable in create array. We've got a pointer to this thing we mallocked in the heap, and then we return it and assign it to this variable up here. This function finishes and its local variables get destroyed, but we mallocked the heap, but we mallocked the array. It's on the heap, it's still there. Okay, so now we're able to return a pointer to this array that's on the heap. Or we can just think of it as an array. We've returned an array. Did I save this? Nope. Okay, and that compiles even, like, we're no longer getting warnings. That's a good sign. Yay. So we were able to create this array. We were able to put data in it and then return it to the main, and the main just gets this pointer to this array. And then it's passed it in and it's printed it as well. So we weren't able to do that until we learnt malloc. Now, have I forgotten anything? I've forgotten a couple of things actually. We should always test if our malloc worked. So I should just check that, well, if it returned null, then I'm in trouble because I didn't get any memory back. And maybe I might want to print out an error message. Maybe I might decide to just exit the whole program and just say there's no point continuing. I'm just going to shut down the whole program. I'll do that this time. And look, it's unlikely to happen in a small program where we've just asked for enough bytes to store 5 integers. The other thing, though, I forgot is, does anyone know what I've forgotten? So it looks like it works fine, but if I compile this with DCC --leak check, which we'll be doing when we're like testing things that you do, and we run it, it's going to tell us at the end, you haven't done your freeing. You've done a malloc on line 21 and you've never called a free for it. And even though our program was able to run to completion and it was fine, we still want you to get used to doing these frees for situations where you might be using a lot of memory, and it's very important. So where do I put this free? Exit. Exit is like, it just actually stops the whole program. So a return ends the function. A return from the main ends the whole program. Exit just ends the whole program. Yeah. And these, when we finish our programs, we can give codes, and typically 0 means, yay, everything went fine. And typically any other code means, uh-oh, something went wrong. And in this course, those codes don't really matter. But yeah, it just kills the whole program. Okay. So yeah, where do we want to put this free? Now the thing is, we've really got to think about what's happening in this program maybe. So I've got this chunk of memory. I asked for it here. I put values in it here. And then I return it, and now I'm pointing to it from here. And I'm printing it here, so he's using it. So I've got to make sure I don't free it until here, right? That's when I've stopped using it. All right, so let's try that. I'm just going to put a free here. Yay, that was correct. Now just say I kind of thought, okay, I'm done. I don't know, maybe for whatever reason, I free it here instead. That's going to be a major problem because I'm freeing it and then returning a pointer to it, and then I'm using it. And DCC has worked that out and given me a warning. It's not always able to work these things out though. If I still go ahead and run it, it's saying, look, you're trying to print out data that you freed. And it says malloc use after free. The other thing is, if you accidentally free things twice, now again, this is a small program, so this is very obvious that we're freeing it twice. But you can imagine if you've got lots of code and you're sort of losing track of what you've done and you free it twice, that's also going to be a problem. Yeah, and this is saying double free. So don't, if you're the sort of person that likes to check if you've locked the door 3 times in a row like I do, that's fine, but don't just free your data a few times in a row in case. Someone's saying, wouldn't it be better to use return instead of exit? It depends what you want to do. I'll do another example where we do return. We can return null from here as well. But it just depends. You might sometimes think there's no memory left. I'm just killing the whole program depending on what you're doing. Okay. So yeah, we've turned this into a heap array that we could return. All right. Now, in this example, we're using malloc. This isn't even in a function, right? This is just the main function, but we're using malloc in a way that allows us to sort of ask the user, well, how much data are you going to store? And this allows us to do a malloc and create an array of the exact size that the user is going to need. I mean, this assumes that the user kind of knows what they're going to need, but sometimes that is the case. So we can make an array of exactly the right size by using malloc like this as well. And again, we just say how many elements times the size of those elements, and we check if it returned null. We want to make sure it's successful. So we can do that. That's another reason we might use malloc in this course. All right. And maybe I didn't point that out down here, but I have before. Even if we've got a pointer to something and your brain is telling you it's not an array, it kind of is, and we can still use these indexes, okay? All right. This example puts all these things together. I'll just go find it. I've already coded it up. So here's an example where I'm using malloc again. And in this case, it's again for an array. But in this example, I'm actually asking the user, how big do I want the array to be? And then I'm passing that into create array. We're making an array exactly the right size that the user thinks they need. I'm checking for null. Now in this case, if Malloc's telling me there's no more memory left, I didn't actually do exit this time, but I've got to return something. So sometimes we will return null from a function to say, well, there's no address here, there's nothing. And that's what I'm doing in this case. But we've got to remember, returning from a function means that, you know, whatever called your function is going to continue executing. So if we return null, then this potentially could have null in it, and we would need to check for null here again. So yeah, you've got to be careful once you've got functions that might be returning you null that you've written or anyone's written. You've got to keep checking for these null values. All right, so here this malloc is being used for two reasons. One, to return an array from a function, and two, we get to do a custom size array. So the user says, I want 20 elements. We build it to house exactly 20 elements. Instead of guessing and guessing too high and wasting space, or guessing too low and not having enough. The cull part. Oh, the null part. Okay, here's an example of null pointers. All right, so here's my own function, because it's hard to get malloc to return null to you. But any function that returns a pointer might potentially return null depending on the context. So here I've got a function and it always returns null. And null is a special value in C that you can that represents no address. So if I said, you know, function f, go and return the address for me, and it returns null, and I try and actually dereference it, and you're going to be doing this a lot, I promise you, in the next topic accidentally. So here, in this case, it's simple. I know for a fact we're going to get null. And then I'm going to do star, which means go to that address. That address doesn't exist. Null means no valid address. And our program is going to crash. So on the off chance that you have a function that returns this special value null, that means there is no address I can give you. I guess it's like saying to me, do you know, I don't know, Mary's address? And I say, no, I don't. You don't end up with an address. You can't go there. You've got to think, well, if they said they don't know, I can't try and go to that address. So what we can do in our code, once we might be getting these null values, is we can just check. Well, if the address that I just got back was null, then maybe, you know, I don't go to that address. Or in this case, I might say, well, if I did get a valid address and it wasn't null, well, I can go to that int and print it out. So you're just checking you really got some legal address that you can go and visit before you try and visit there and crash your program. Okay? And you might do something in the other situation, but the idea is you're going to be having code that checks whether pointers are equal to null, whether they're not equal to null. If they are equal to null, you can't use them. You can't go and dereference them. You can check if they're null, that's about it. We don't always have to do it, but once we're dealing with functions like malloc where we know it can return null, fgets, we know it might return null. If we're using the return values from them and we know it might return null, we should do it. If we ourselves might be returning null in our own programs, and we'll be doing a lot of that, then we should check it too. So in this example, if malloc returns null, then I'm returning null. So this better check for the null that I might return it, etc. Well, if something's equal to null, you might want to do one thing. If it's not equal to null, you might want to do another thing. In this course, we will never really use all the memory in the heap unless, and I've got an example here, unless we do something like this. So this sometimes people do by accident. Like, you know how sometimes you might want to do one malloc, but then you don't realize that you've done it inside a loop or something. Or maybe you are planning to keep asking for memory again and again like this. But this kind of thing, this is when malloc might return null and you might run out of memory. Now on the CSC machines, they've got sort of safety mechanisms that I think will just step in and just kill my program before malloc returns null, because it's not going to let people like me suddenly start hogging all the resources on the machine. So in this case, malloc didn't get to return null because the CSC system killed my program. But sometimes it's a little bit like, you know, if you've got cups in your home, you might have 30 cups in your home and you might never have 30 people in your house or more to use all the cups. But if you keep taking one cup at a time and you never wash it up and put it back, you're going to run out of cups. And the same thing can happen in a program. If you malloc memory but you don't free it and you're not using it anymore, then you might run out of memory, even though technically, you know, you could have freed it, given it back, and then there'd still be some there, right? So in this case, if we could malloc our memory, use it, then free it, just like, you know, at home, if you, like my mum always used to try and teach me, you know, put the cup in the dishwasher, don't leave it hidden in your room or something like that, then you don't run out of the cups. If you free your data when you're finished with it, you might not run out. You won't run out in this situation. But yes, sometimes you might legitimately, for some big game, really be testing the boundaries of the systems. Yeah, malloc is happening as the program's running. You get a chunk of memory for your program when it's running. Part of that memory will be used for the stack and the local variables. Part of it will be allocated for you to do, you know, use malloc for. All right, now I've done an associated free. This is going to run for basically forever in terms of the memory. It's like taking a cup, washing it up and putting it back. You're not going to run out of cups. But in this example, is someone knocking at my door? In this example, yeah, look, this might not run forever if you try it because there might be an integer overflow, but that's beside the point. All right, so that's malloc. Now, usually this isn't an issue, but yeah, you might do a bug like this, putting a malloc in a loop, and you might see your program getting killed. I don't know. What's the time? Oh, I've still got plenty of time. So look, we could be mallocing all sorts of things. So far we've done a few arrays, and I'll show you structs in a minute, and just a little bit more about the size of operator. Looks like a function. We can get the size of pretty much anything. I can ask it for the size of a variable and it'll work out how many bytes that variable's stored in. I can ask it for the size of various types. I can, you know, multiply things because I want 10 integers. We've seen that. I can get the size of structs. I can get the size of pointers, whatever. And yeah, we don't have to memorize what it's going to give on our system, but this just gives you, you know, just shows you can use it in all these different situations. So that's a reminder of size of. All right. So let's do an exercise. This is a very, very, very important exercise. So over the next few weeks of your life, you're going to be mallocing and returning pointers to so many structs. It's really something you're going to need to know how to do. So here's an exercise. Just, our first struct we're going to malloc and return a pointer to. So let's go do it. Oh, good. Okay, so let me get rid of that. We're writing a function. Maybe I should show you the struct. But yeah, we've seen this struct a lot. But basically, we want to create a struct in here and return a pointer to it. So it's going to have an X and Y component that we're going to set. So if somebody calls this function and passes in 10 and -1, we're going to set the data inside it, and then we're going to return a pointer to it. That's what this function is going to do. So the first thing is, if you just set off and do something like this, struct coordinate, if you do something like this, we're falling into that old trap where we're creating a local variable, and then we're returning the address of it. And then when the function finishes, it's destroyed. So hopefully it's clear. We don't want to do something like that. We want to use malloc. So malloc's always going to return a pointer. So I'm creating something that a pointer variable that can store the address of a struct. And I'm going to call malloc. To know how many bytes I need, I'm going to use size of. And I could put the variable name in, but I'm going to put the type in, which is struct coordinate. So this line here is going to give me a chunk of memory. Oops. I hope a chunk of memory big enough to store one of these structs on the heap. So when the function finishes, it still exists. Now, when we're using this function, we're going to be passing in values to store in this struct. So for example, X might be 10, Y might be Y -1. So what we want to do now is, look, let's just check if our malloc worked. Now we don't always have to type out of memory, just making it clear what's going on here. Okay, so let's assume that it does work, right? What are we doing? I better get rid of my drawings that are in the wrong place now. I want to take this value, maybe I'll draw this. So I've got my X and Y, which are on the stack. I've got this new coord variable, which is pointed to this struct I've just malloced. And let's imagine the X that the user gives me is 10, the Y that the user gives me is -1, or the main function gives me. What I'm trying to do is I'm trying to set the values in here, the X and the Y within this new struct that I've done. So again, I've got a pointer to a struct. Instead of using dot with a struct, I've got a pointer to a struct, I use arrow. So I'm saying, let's set the value inside my new struct to this input into this function. So we're putting this value into here, and it, in this case, I'm pretending it's 10. And we do the same thing for the y value. We're going into the actual struct we've just created and setting the x member to have whatever input this function has been given, and we're sticking it into this struct. So once we've done that, we've mallocked our struct, we've basically initialized the data that we were given, and then we return it. And we don't use address. This whole variable is storing an address. It's a pointer. So this matches this, we just return it. Okay, then when our function finishes, because it's on the heap, it'll still be available as long as we return it and whoever called our function stores it somewhere. So if I was up here and I was using it, I might say struct coordinate if I did indeed want it to have 10 and minus 1 in there. Yeah, and when it returns this pointer, I get the pointer back here, I'm assigning it, and now I've got a pointer to this thing which is on the heap. Okay. So I've mallocked a struct and returned it. If I've got a function that can print that struct, oh, I haven't written this function. All right, let's try this. I've got a pointer to this struct on the heap, and I'm just printing it out. Well, it contains two integers. I might put a comma between them. I'm going to print the x and the y. Because I've got a pointer, I use arrow, not dot. Okay, so this should print out 10 minus 1. Okay. Up here, I've called my create coordinate function. I'm calling my print coordinate function. When I call my print coordinate function, it's expecting the address of a coordinate. That's exactly what my variable contains. So I just pass it in as is. That should print it out. Let's try it. Okay, so that compiled. And that seemed to work. Now I could do more. Oh no, I might not do that. Let's do have another coordinate. Create that, print them. Okay, what have I forgotten to do in this program? Yeah, I haven't freed anything. What do I need to free? And where do I free it? I'm seeing lots of frees, which is great. Now let's just check it with DCC leak check, even though we've realized, hang on, we haven't done any frees and we know we've done mallocs. We run it, it all works fine, except then it complains. On line 41, on some line, oh, I think I've edited it. Anyway, we're doing a malloc that we're not freeing, and they're saying it's this line here. But what do we free? What am I freeing? How many mallocs have I done? Yeah, I've actually done 2 mallocs because I've called this function twice. So I need to free my coord and then my coord 2. And the thing is, this will work. Well, it should. I shouldn't get too overconfident, right? Let's check it. That'll work, and that's not complained. But if we were really in a situation where we really needed every ounce of memory that we had, we could potentially free this a bit earlier. And obviously in our situation, it doesn't really matter. But just say we're running tight on memory, we might want to free it here because we weren't using it again. If we're not that desperate, down here's fine. Okay. Any questions about that? The other thing that technically we should do that probably won't be an issue in our code is that my function could potentially return null. We know that it's not really going to in this situation, but still I've got a function that could return null. So if it did return null, this is going to break and then I shouldn't free it. So I will be doing lots on this and we will do cahoots on it as well. So we should potentially be checking that this isn't null, right? Or if it's really that vital that our program can't go on, we can just exit the whole thing and say out of memory, goodbye, that's it. We'll do different things in different contexts. All right, so look, the main thing though is you'll be doing heaps of these things with structs, but the main thing is that, where's my slide? We malloc something, we check if it's successful, we use it in some way, and we free it. Okay, they're the main concepts. Why do we use malloc? Well, it's on the heap. We can return a pointer to something on the heap from a function. We can also malloc things as we go and malloc more and more memory when we need it and free it when we don't need it. We're not locked in to a set amount of memory. Somebody just said, why did I do exit? I was just saying, if you return null, that's fine. It doesn't exit the whole program though. It'll potentially return null to the main. And I was just saying, sometimes we might just want to kill the whole program, but it depends what you want to do. So you can return null. Sometimes you might just say, if you don't have memory for that, I'm out of here. And that's when you'd use exit. But we'll see both things. All right. All right, that's, oh no, one more thing. Actually, I might skip realloc for now. And we can do it tomorrow. But let's have a quick look at multi-file projects. This isn't so hard on the brain as pointers, but basically, we've been squeezing everything into one file, but big programs are often spread out over multiple files. And the benefits are just, it's easier to find things and read them if we move them into sort of related files with related things. It also means you can potentially write different modules and test them separately before you put it together into your program. And we've already been doing this because every time we hash include, we're actually borrowing code from other files. So we hash include std.io. That's code we did not write. we hash include the .h file, and then when we compile our program, it gets linked together as well with all of that C code that implements printf and scanf. We've only been doing it on the standard C libraries, which are just set up for you, but you can also make your own modules and libraries and hash include your own code. And this allows us to join projects together, and if you have colleagues you're collaborating with in the workplace, don't collaborate please on assignment 2. People can work together more easily when we've got things divided up into different files. We could use that code again for something else, etc. Now, assignment 2 will be a multi-file assignment, so you will need to do this. It's okay though, it's not too hard. Assignment 1 wasn't. Don't suddenly go and change your assignment 1 now, especially because it was due yesterday. Do not split assignment 1 up into multiple files. But assignment 2, you'll actually be given multiple files. Now, typically in a multi-file project, you'll have header files or .h files, similar to like what you've included from std.io and now stdlib, string.h, all those sorts of things. And then you'll have the .c files, which actually have the C code for those header files. So they'll often be in pairs. And then if you want an executable, you're going to need a .c file that has a main function in it. Okay. Now, what do we put in our .header files? Typically, our .h files will contain prototypes of all the functions that we're actually going to implement in the .c file. Hash defines, enums, structs. So a lot of that stuff that we've been putting up the top of our main, if there's a lot of it and it's related, we could put that in a .h file and make it a little module. The .h file does not contain like executable statements like while loops or stuff like that. So the H files also, if someone was going to use your library or your colleague was going to look at your .h file, they should be able to have enough information in there to work out what your module's doing. They'll know what functions you've written, all the sort of hash defines and stuff like that that might be useful. And it also lets the compiler know. So when the compiler is trying to compile your code, it needs to do syntax checking and type checking. It can get that information from the .h files as well. Now, what do you put in your .c files? Well, per executable program that you're trying to compile and create, there should only be one C file with a main function. But you might have lots of other C files that just have implementations of functions in there. All right, and then in our .c files, we're going to need to hash include the relevant .h files. And you've been doing that already. You're including relevant things like std.io.h. But now you might be hash including your own .h files that you're using. When you're using system ones, that's what we've been doing. We're using those angle brackets. When we're using our own ones, we're using quotes. So let's have a look at this example. Let's get rid of other program for now. All right. So just say I decided that I've got all of these, great integer array functions that we wrote a few weeks ago. And maybe I think that it would be useful to put in some kind of module. I've called it arrayutilities.h. Now, in this example, all I've got are prototypes, but in some situations, you might make a Pokemon module or something, and there might be enums and structs and hash defines as well. And then I've got the actual code for this stuff somewhere. Okay, here it is. So this actually has the code for all of those things I was claiming, you know, that I have prototypes for over here. If it's our library, we're the ones that are writing the code for it, right? So I've got all the code in here. Now, if I just try to compile all of this, it's going to say, hang on, this is not a complete program. It does not contain a main function. So this code on its own is not a standalone program, but it implements a whole bunch of useful functions. Now over here, I got a program and I'm hash including these array utilities.h. So the compiler knows that if I'm talking about, you know, read data, it knows about it, right? Because it's in array utilities.h. Just like if I type printf, the compiler knows because it's in stdio.h and it doesn't give us a syntax error. So here I'm actually using the functions in this main to do something. But again, if I just compile this on its own, this isn't a whole program either. So unlike when we're using libraries like the official libraries, when we're using official libraries like std.io, it'll automatically go and get all that code and link it together. If it's my own kind of library or .c code that has functions in it, I'm going to actually have to compile those two things together into one executable like this, right? So the basic rule is you hash include the .h files in your C files, but you don't compile the .h files. You compile all of the C files relevant to that program into one thing like this. Oops. Okay, so that's all it really is. And it makes things nice because I can have all of these sort of array utilities in one .h file and one .c file, for example. And I could have a whole bunch of these .h and .c files that I'm using. All right. And of course, I might use these array utilities in another program. So I might have some other program here that I've called other program. And it also might use array utilities, but it's got a main, right? So you could not try and compile all of these files together. This other program that has its main, but it might also use these array utilities. That's okay. You compile these two parts together like this. All right. Yeah, but that's kind of the main thing. Yeah, we're not worrying too much about static variables in this course. So when you get your assignment 2, there will be different files, and you're going to have a situation like this where you've got to compile them together like this. So that's all you really have to worry about. And you'll be implementing, obviously, some C code. No, it can't have two mains. It can't have two mains. If you had two programs with mains, they're two separate programs. You can't combine them into one executable. So in this example, this has a main, this has a main. They both use utilities, which doesn't have a main. You can compile this into one program, and you can compile this into one program. You couldn't compile both of these things into one program. You can only have one main per executable. But you might have lots of main programs that are using your wonderful library, but you'd have to compile them separately. Yeah, array utilities.h gets hash included, and then the utilities.c would have to be compiled in with the rest of the program. All right. So what did we learn today? Well, I don't know what anyone learned really, but this is what we covered. We didn't do realloc. We can do that tomorrow. It's not that big a deal. But now we know structs, pointers, and malloc and free, we're ready to learn about linked lists. And if you don't know what linked lists are, then, you know, that's not going to mean too much to you at all. We'll find out tomorrow in our catch-up lecture. All right, so thank you very much. Thanks for your patience with the situation yesterday. I'll see you, if you can make it online, 5 to 7. If not, definitely watch the recording because it's important content. Thanks, everybody. I should let you go. We're running over time, and you know, the content we did today is not easy. So if your brain's feeling a bit overworked, mine is too. It's all good. All right. See you later. See you tomorrow. Bye-bye.